real exam questions. Question 48, it's about the serviceability limit state. Determine in nevertheless the concrete compressive stress and steel stress in simple bending as a function of the uh, reinforcement in tension, the alpha, the width of the section, the effective depth, and the bending moment, and this for a rectangular section. You can ignore the contribution of the compression reinforcement, so AS2 is 0. Make a sketch with strains, stresses, and forces. State the 3 basic assumptions. Determine the concrete pressure height as a function of the geometry and the reinforcement. Determine the steel stress and the concrete compression stress. So we start with the rectangular cross-section with only tension reinforcement. The cross-section has a depth of h and a width of b. The reinforcement is there. The point of gravity of the reinforcement is g1, and the effective depth is d. Now we'll go over to the strain. This is the strain before loading. This is the strain after loading. We will just see it now. And this is the strain after loading. The maximum strain is epsilon C in the concrete. It's the compression in the concrete. And the maximum strain in the steel is epsilon S1. And this for a concrete compressive depth of X. Now we go over to stresses in SLS. We have the stress in the tension reinforcement. We have the compressive strength in the concrete, no tensile strength because this is ignored. And then we go to forces. Of course, the external force is the concrete compressive force and the steel tension force. The distance between is the lever arm Z. The distance of the concrete compressive strength to the top fiber is x over 3 because this is a triangle. And this must be in equilibrium with the bending moment MSD. Assumptions, we use Bernoulli, a section before loading stays a section after loading. And for this, we can say that this angle alpha or the tangents of this angle is equal to tangents alpha of this angle. So the tangents alpha of this angle is epsilon c divided by x. And on the bottom, it's epsilon s1 divided by this, which is d minus x. The second assumption is adhesion. Because of adhesion, alpha is equal to this modulus of elasticity in the steel divided by the modulus of elasticity in the concrete. And elastic behavior in SLS. So the strain, or no, the stress in the reinforcement is equal to the strain times the modulus of elasticity. That are the 3 assumptions that we need. We first look at translation equilibrium of the forces. It means that the force in the concrete must be equal to the force in the reinforcement. And the total force, compressive force in the concrete is of course equal to sigma c times x divided by 2 times of course the width of the section. And sigma c is equal to epsilon c times EC. We will express everything in function of epsilon c, the strain in the concrete. The total tensile force is the cross-section of the reinforcement times the stress. The stress is E times epsilon, and epsilon S1, we will express it in epsilon C. We can do that because of the Bernoulli relationship. that we have made on the previous slide. So then we have this expression. Now NC is equal to NS1. When you do that and you work it out, you arrive at a quadratic equation which looks like this. This quadratic equation has one positive solution, which is given by this formula. You see that the depth of the compression in the concrete, X, is only dependent on the geometric characteristics of the section. There is no MSD or whatever in this formula. So translation equilibrium gives us the total depth of the compressive force. The rotation equilibrium on those forces, we will have a rotation equilibrium around the normal force of the concrete around this axis. So we have that the MSD, the bending moment, MSD, is equal to NS1 times Z, the lever arm. NS1, we know that is the cross-section of the steel times the stress. And this gives us with Z equals, of course, Z is equal to B minus X over 3, because this is X over 3. The stress then in the reinforcement is then given by this equation, which is bending moment divided by the lever arm and the cross section of the steel. And we replace Z with D minus X over 3, and we have the formulation for the stress in the tension reinforcement. The bending moment can also be taken around the tension reinforcement or around the compression reinforcement. Now we will take it the bending moment around the tension reinforcement. It means it is NC times Z. NC is of course B, the width, times X times sigma C divided by 2. And from this we get the stress in the concrete, which is equal to this equation.